In this video, we're going to cover section 4.8 on the conformations of monosubstituted cyclohexane. So as we saw in the previous video, cyclohexane tends to adopt its most stable conformation, which is called the chair conformation. And this is the chair conformation shown as a bond line structure. Now, when we draw the cyclohexane ring with only one substituent, that is, one group other than a hydrogen, there are two different conformations that can arise, and these conformations are in equilibrium with each other. So as we saw in the previous video, we would refer to this group here, this group X, as being in the axial position in this particular chair conformation. Whereas in this particular conformation, we see the chair has the substituent in an equatorial position. And so that will be the key difference in these conformations that can occur for monosubstituted cyclohexanes. We will see an equilibrium established between the substituent on the cyclohexane ring being in an axial position and that of the substituent in an equatorial position. Now, this equilibrium between these two different conformations, this is known as a ring flip. So a ring flip is a conformational change in which one chair conformation is converted into the other. And this is accomplished through a rotation of all the carbon-carbon single bonds. So as you can see in this figure, we have the cyclohexane ring, a Newman projection for cyclohexane, and attached to the ring system is this group X. And as shown, this group X is in the equatorial position. Now, if we undergo a ring flip, that is a rotation of all the carbon-carbon single bonds, the new conformation is shown on the right-hand side. And now we see that that group X is no longer in the equatorial position, but has undergone a conformational change, which puts it in the axial position. So the conformational change of the ring results in all the groups that were axial now being in the equatorial, and all groups that were equatorial prior to the ring flip now are in the axial position. Now this is a little bit difficult to see with this particular figure. So what I'm going to show you on the next slide is a virtual model kit, which there is a link to in UR courses. And within that, they have a short movie which shows you the ring flip for cyclohexane. So if you go to UR courses and go to our course page, if you scroll down to useful links, one of those links is the ChemMagick Virtual Molecular Model Kit. So if you select that, a new window will open and the virtual model kit is shown here. So select that. And this kit is quite useful for looking at structures in 3 dimensions. And so if you click on an atom and hold it and then rotate on your trackpad or your mouse, you can see that you can move this molecule around in 3 dimensions. Now within this kit, there's also some models that have been drawn and made into videos or animations. And one of those is the cyclohexane flip. So that's the one I wanted to show you today. So if you select cyclohexane flip, that will load the animation into the molecular model kit. You can see here, it will automatically start to undergo this ring flip, this chair conformation, where we have all the bonds rotating between the different conformations. And so here, this tail will come up, the head will go down, and if you follow the various hydrogens shown here in white and pink, is that in each structure, you'll have all the hydrogens in the axial position, and they will ring flip to all the equatorial positions in the new chair conformation. And so the video ends, and I just want to show you that this is the kind of the chair that we, let me go over here. This is the chair that I often will think of, that side on, you have this is your seat, and what's shown here is the head of the chair, and what's shown here is the foot of the chair, if you will. And so when we look at cyclohexane, we see that what's shown as pink hydrogens, these are all in the axial position. And at every carbon, there is a hydrogen that's in the axial position as well as one in the equatorial. So what's shown as white are all the hydrogens around the equator of the ring. So I hope that this molecular model kit can help you see these particular conformations. And again, if you want to play the video again, just select the animation from this site and it will reload it. And again, if we track this particular hydrogen, it's in the equatorial position currently. The ring flip will begin, and when it finishes, that hydrogen will be in the equatorial position. So I hope this was helpful for you to see the three-dimensional structure of cyclohexane and to get a better sense for what we mean by this ring flip. So when two chair conformations are in equilibrium, the lowest energy or lower energy conformation will always be favored. And for monosubstituted cyclohexanes, it will always be the case that when that group is in the equatorial position, that chair conformation will be the lowest energy conformation. And that's because we have interactions that can occur between the group in the axial position, in this example, the methyl group, with other hydrogens present in cyclohexane that are also in the axial position. And so as you can see, for this methyl cyclohexane, 95% of the time, the conformation will place that methyl group in the equatorial position. Only 5% of the time will methyl cyclohexane place the methyl group in the axial position. So when a substituent is in the axial position, there's these steric interactions that can occur with other axial hydrogens on the same side of the ring. And so this diagram shows you the cyclohexane chair conformation and this group X, and neighboring that or through space, there are hydrogens that are also parallel to the group. So we have not only this X group being shown in the axial position, but we also have hydrogens which are also in the axial position. These hydrogens happen to be 2 positions away. So we refer to this as the 1,3 diaxial interaction, in the sense that if this were carbon 1, the first axial hydrogen as we go clockwise around the ring is at the 3rd position, or if we were to go counterclockwise around the ring, this carbon 1, 2 not being shown so clearly, and 3 is where this hydrogen is located. So that's where the term is derived from, this 1,3 relationship between the group X in this example with the hydrogens on the same side of the ring. So these 1,3 diaxial interactions are what gives rise to a less stable conformation when that substituent is in the axial position. The substituent, the electron cloud around that substituent, is basically trying to occupy the same space, region of space, as the hydrogens. And so there's a steric effect. There's a steric hindrance associated with that. So again, the preferred conformation for a monosubstituted cyclohexane is that that group, that substituent, lie in an equatorial position on cyclohexane and not the axial position. And here's some Newman projections to kind of show you where this interaction is arising from. So you may recall when we looked at butane, the Gauss interaction, there was some steric hindrance, steric strain associated with those 2 methyl groups being next to each other, having a dihedral angle of 60 degrees. When we look at a monosubstituted cyclohexane, like methyl cyclohexane, again, it's these interactions between the methyl group and the hydrogens located at position 3 that give rise to this steric hindrance or the steric strain. And so when there's a ring flip, a conformational change that puts this methyl group in the equatorial position as shown in this Newman projection, there are no longer those interactions, and interactions are minimized with other carbon-hydrogen bonds as well. So again, the 1,3 diaxial interaction will be present when your R group, your substituent, is in the axial position on cyclohexane, and the preference will be for a ring flip, a conformational change that will put the group in the equatorial position, and that will be the predominant conformation at equilibrium. Now we can look at the effect of the substituent on this ratio of the group being in the axial versus the equatorial position. So here we can see that the size of the group is really important in establishing the ratio between equatorial and axial positions for that group on cyclohexane. So if we start with the chlorine atom being quite small, we see that 70% of the time the conformation of chlorocyclohexane will be in the equatorial position, and 30% of the time that chlorine group will be in the axial position on cyclohexane. As we increase the size of the substituent to the hydroxyl and the methyl, we can see that the ratio of the equatorial is increasing at the expense of the axial position. So for methyl cyclohexane, we have this 95:5 ratio between equatorial and axial. And by far, the most significant difference is when we have a tertiary butyl group, as shown in this figure, this bond line structure. The tertiary butyl group, over 99.99% of the conformations of cyclohexane for this particular compound will place the tertiary butyl group in the equatorial position. Only 0.01% will be in the axial for this particular compound. So if you have any questions about the conformations of monosubstituted cyclohexane, by all means send me an email, or we can set up a Zoom chat, or start a discussion in our forum. Thanks.